In today's lecture number 25, we start our discussion on alternating direction implicit method, and we talk about a general elliptic equation which could represent either the Laplace's equation or the Poisson equation or Helmholtz equation. And we notice that it requires discretizing the Laplacian operator, and we will identify that this Laplacian operator is best discretized by casting it in a self adjoint form. And once we have this discrete form of general elliptic equation, we show that the self adjoint form actually leads us to a diagonally dominant matrix. And we also notice that this ADI method actually utilizes the analytic solutions of tridiagonal linear algebraic equation. That is what we actually do in a two dimensional problem. We split it in additive fashion, and in each step of the ADI method we go along one particular direction, and since the directions are alternated, that is the reason that we have called this method as alternating direction implicit method. And we discuss about its error propagation properties, and we find out that this in ADI method what we actually obtain is introduction of acceleration parameters to further accelerate this alternating direction approach. And this acceleration parameters are of two kinds. One set was given by Piesman and Rachford, and the other set was given by Wachspress. And these acceleration parameters are found out with the help of a pair of theorems due to Gershgorin. That is what we are going to talk about today. Get back to our discussion on ADI method. Okay. See, we make this observation that the ADI method is similar in spirit to line iteration method. We have seen line iteration method is the basically really the method of choice till 1950s, because they were showing a progression in terms of computational efficiency and speed and benefits. So, people were doing line iteration. However, it was also noted that the strategy by which we go along in choosing these lines favors boundary conditions from one side or the other. So, that is where this idea came upon, that if we keep switching this direction of solution, then what will happen is we could in an unbiased manner bring in the boundary information from all sides, and that is what is desirable for a boundary value problem. So, that was the whole idea. The second thing is, of course, I noted to you that most of the time that elliptic differential equation, partial differential equation that we solve involves Laplacian operator or the biharmonic operator. Wherever they appear, they of course appear as a power of 2. That is the reason that you get complex conjugate as a characteristics, right. And what you note that representing this Laplacian or the biharmonic operator, you like to do what I have noted down here as a self adjoint form. We like to have something in a particular fashion that gives us certain numerical properties. Okay. What are these numerical properties? Some of which we discussed in the last class itself, that we want the associated linear algebraic equation of the following form, and we should have some nice property for this matrix A, and one of the nicest property that you can think of is the matrix should be symmetric, it would be positive definite, right. That is what we talked about. So, to at least achieve symmetry, this form of the PD is very desirable, because for example, let us investigate one of the point constituent point I have written here. See what we have done here, we have written it down in a form like this. This is what we always would like to do. So, if I have the Laplacian operator of this kind, I would rather like to write it in this form. Okay. This is something like your self-adjoint form we are talking about here. See, this A is like your F and C is like your G. Why we do that is very apparent when you start looking at the discretization of that term. This term here has been discretized in this manner. So, how it has been discretized? Let us take a look. Let us say this is my one of the coordinate direction, this is the other one. So, let us look at a segment of a point. So, this is my ijth point, that is where we want to discretize the term. Now, what we try to do is we try to have a system of discretized equation which remains unbiased, right. So, if I am trying to discretize in the x direction, so I should not have any asymmetric coefficient in the discrete form. That is what we mean by unbiased nature. How do I do that? That we have already seen that if I do a kind of a central differencing. So, here in this part, this del u del x has been written down in this form. What has been done? We have taken the point half a node to the left and half a node to the right, divided by the spacing between these two nodes. That is why this is your equivalent CD2 formulation, is not it? See, we have taken half a node to the left and to the right, and of course, we are focusing our attention on the ijth node. So, we have kept A here at the ijth node. So, basically what we have done in the first step, we have invoked these 2 points, right. So, this is my ith node and this is my jth line. So, in the first step I am discretizing del u del x by taking this point at that point. That is what we have done. Well, you can then proceed further. Now, you have this as the function and that you are differentiating. Again you do the same thing. Take let us say, let me take this first set of point a I j times u I plus half j. If I do that, then what I am going to do? I am going to take this one shifted half to the right, that is why I have written a I plus half j, and then that is multiplied with this quantity u I plus half j, that has to be differentiated, and if I take a half a point shifted to the right, that will give us u I plus 1, and if I take half a point to the left, that will give me u I j. So, this is this part is coming from the first product and the next part comes from the second product. Now, this A is now shifted half a point to the left. So, that is why we have written a I minus half j, and of course, u I minus half j, if I differentiate, I will get half a point to the right. So, that will be u I j, and half a point to the left would give me u I minus 1 j. And of course, there was one delta x, and this differentiation would bring in another delta x. So, I have the whole thing divided by delta x square. So, this is the point, but we will write it like this. We write it like this, and you can very clearly notice that discretization of this term invokes the unknown at 3 points, which are those: the central point itself u I j, then one point to the right u I plus 1 j, and this is this. Now, what you notice though, that there is some form appearing from this discretization. This is what we have tried to explore here. Let us for the sake of simplification of notation describe H as delta x and K as delta y. Then the quantity that we were discretizing was del x of A del u del x. If I multiply that quantity by H k, and I purposely multiplied it with a minus sign, so that the diagonal term appears with a plus sign and the off diagonal terms appear with a negative sign. You recall we enunciated some property of A matrix to be property A we called, and that was desired that your diagonal elements are positive, off diagonal elements are negative, and then they would also have the diagonal dominance property to get a good iterative solution strategy. Okay. So, if I write it like this, so if I write it there at m nth node, I get this structure, and it is very easy for you to clearly see the tridiagonal matrix appearing here from the first term, which I called as H u, right. So, H u here is written in this form. Okay. So, basically we keep writing it for different values of m starting from the first interior point. So, if I look at the boundary point as u 0 n, then I will start this discretization from u 1 n, and when I do that I will see u 1 n would be the my beginning starting post, and that would have a point u 2 n and u 0 n. U 0 n let us say is the boundary point. So, that would not stay on this side, that goes to the right hand side, right, that is a known quantity. So, when I write in terms of the unknown, then the first line gives me 2 entries that will have the entry that would be here 2 b m n, and this quantity would be on the super diagonal, that is at minus a m n. Now, of course, once you move away from the near boundary point, you start having all these 3 points. So, for example, point 2 onwards you will get 1, 2 and 3, and then you start getting this regular tridiagonal structure, right. So, this is what it is. Now, what is this AMN? AMN, see, remember this was divided by h square. So, when I multiply by h k, that would give me a factor of k by h, right. So, I have this entry is given as a constant multiplier k by h in all 3, and what we also notice a particular nice property that the off diagonal terms, if I take their magnitude and add it up, that is what gives me the diagonal quantity. So, 2 b m n is nothing but equal to a m n plus c m n. Why do we do that? Well, you recall that was one of our requirement for diagonal dominance. We wanted that at the most the diagonal term in magnitude should balance the sum of all the off diagonal term, and that is what is guaranteed by this kind of discretization, right, because the central entry is always balanced by this. Where do you get strict inequality? You do get the strict inequality on the first row and the last row, right. So, by doing this kind of discretization, what you are ensuring is that you would have a very nice diagonal dominance property of the system. Now, look at the other term that we had, something like this. There we had written like del y into c del u del y, again you multiply by minus h k, and you will get in terms of these coefficients alpha, betas and gammas, and they also have the same kind of property. Now, you notice that here the constant multipliers are h by k, okay, and that same property is shared here. The diagonal entry in magnitude is sum of the magnitude of the off diagonal entries. So, if you now go back and take a look at the equation 60, we have just now talked about discretization of this path In addition, we will have a term like this G into U. Where do we get it? Those of you who are familiar with little bit of electrostatics, you would know that is the kind of term you get in Helmholtz equation. Okay. So, you would get this kind of term there. So, that will be like if we are discretizing at the point I j. So, this will be just simply G I j times U I j, and this is your some kind of a forcing that you get in Poisson equation. Poisson equation you get del square f equal to g or something. So, that right hand side the function s is that term that accounts for this. So, in a generic sense, this equation 60 that we have in front of us is a potpourri of everything. You have the Helmholtz equation as a special case, Poisson equation as a special case. You can also treat it as a Laplace's equation. Well, for Laplace's equation, of course, G and S will be equal to 0. So, this is what we are talking about. Now, having discretized those second derivative terms in the self adjoint form, we get this as the finite difference analog, right. We had h times u giving us the first set of term del del x of a del u del x term. So, that is that h is there. Then this is the second term, and the term I told you which makes it akin to the Helmholtz equation g times u adds on to what I have written there as a capital sigma, right, k h times g m n. I have multiplied the whole equation by k h. That is what we have done. If you recall, when I wrote in the previous slide, I did purposely multiply all the terms by h and k, okay, so that certain symmetric nature show up. So, what happens is that sigma u that we are writing here is basically h k times g, and the forcing term on the right hand side will be h k times s evaluated at the point in question m n. Okay. Now, once I write this discrete equation 64, you can place where each of these terms go. For example, the g terms, where does it go? It goes to the diagonal, because we are looking at the nth point that goes along the diagonal, right. So, that sigma u would actually add on to the diagonal entry, right. So, that would actually help the diagonal dominance property. If I have without the g term, already we have shown that diagonal dominance property is there, then in addition to that, if I add this g term, this will strengthen the diagonal dominance property. Okay? And we have already noted that such diagonal dominance aids in convergence. So, let us make our job a little more tougher. So, let us drop the g term. G term is easy to make, I mean it automatically makes your life easier. So, let us try to investigate a case where it is somewhat little more challenging, and we drop that g term, and instead we start looking at this equation 65. So, basically it is nothing but an attempt to solve a equivalent Poisson equation. We are solving a Poisson equation here that is given by 65. This is the basic thing that we have done. So, what is new apart from the discretization? What is new? Well, this is where the people working in the area of ADI came up with the idea that we could split this equation h plus v operating on u to provide that right hand side k in two steps. What we do actually is given in equation 66a and 66b. In the first half step, I add du term on both sides. Then what happens? On the left hand side, I have h plus d into u, and right hand side k was of course there, vu has been put on the right hand side, but since I have added a plus du, I again here add a plus du here. Note the minus sign together will make it. So, we have just simply added the same term on the both sides, right. What is the structure of H plus D matrix? It is still a tridiagonal matrix, right. H matrix itself had some bare bone diagonal dominance property. To that we are adding something as D. So, if D and E happens to be diagonal matrix, then we are adding to the diagonal dominance. Then what we are basically talking about 66A is what? It is a line iterative method, is not it? What is your H operation? Is this derivative. See, basically we are looking at this equation now. This is what we are trying to solve, right. So, from here in a discrete form I get H u, and from here we get discrete form V u, right. So, that is what we have written there. 65 is H plus V u. Now, what I am suggesting to you that put this term on the right hand side. So, what will happen, then I will get this. Okay. To that, so this itself is going to give me a tridiagonal form. So, to that I am adding a entry which enhances the diagonal dominance on the left hand side. So, what we end up doing actually then, we are basically writing it exactly like what I have written there in 66A. So, what happens is I can now solve that 66A along the j equal to constant lines, right. That is what will amount to. That is what will amount to. So, basically what we are suggesting that we will be solving line by line in this fashion, and when I solve that, that would be like solving H u is equal to k minus V u. That is what we do in line iterative method, is not it. We put the y derivative on the right hand side and we keep solving along these lines, horizontal lines, and march. That is what our line iterative method has been designed to do. So, now what we are doing, making that line iterative method little more stronger, and that is why we are adding this D matrix, right. So, that is what we are doing in this thing. Now, what happens is, of course, if H matrix was little hypersensitive, that it had not a very well conditioned property, by adding the D we have ensured that we would not have problem in solving this equation. So, because H plus D would now be a well conditioned matrix, it can be inverted in a mathematical sense, computational sense. So, that is why I am calling it as non singular. Okay. So, that is the first step. I keep solving it like this. I go from line to line like this, stack it up. Now, in the next step, next half step, what I do is I change my direction. Now, I would be solving it in this fashion. Okay. That is what that second equation implies, that V plus E into U is this. So, it is basically the same thing that we are doing, treating. Now, what we could do is we could put in now some kind of a iteration index on this. So, that is what I have done. What I have done is written it down here, what Peaceman and Ratchford suggested, that you purposely take this D and E matrix as strictly diagonal matrix. And how do you do that? Well, you just define D and E is equal to some acceleration parameter. We will talk about this acceleration parameter shortly, which is given the notation here, rho n times the identity matrix. Then I said we are actually doing this. So, if I have a solution at the kth level, Solving 66A is equivalent to solving this. So, I get a half step solution which I am calling it as k plus half. Okay. Having obtained that k plus half solution, then I go to the next half cycle. That is now the forcing term, and I solve this equation, and that completes a full cycle. So, first I do a vertical sweep followed by a horizontal sweep, and that constitute a one operation of ADI method. Okay. And why did we do that? Well, that is what I have been suggesting to you, that look, the tridiagonal matrix plays a very central role in computing, and this two matrices H plus rho k I and V plus rho k I, they are both tridiagonal matrices, right. Now, if we can choose this rho k with lot of care, then we could not only ensure diagonal dominance, we can also control error better, and that is what we are going to study now. Okay. How the choice of this D and E matrix actually influences the success of the method. So, if I have chosen those half steps and have rewritten those equations, but now I am saying look, I have performed, let us say, infinite number of such operations. Okay. Once I have done that many operations, then I do not write it k plus half k, etc. Everything is at the convergence, they have become indistinguishable what you have on the left hand side and right hand side. So, this is what we get. 68A and 68B are the status of the system at convergence. Now, I can denote an error vector which I have shown here for the k plus half step, that will be the converged solution minus the current solution, right. If I do that, then what I can do is I can subtract this two equation from my primitive equations, right, in 67, and subtraction would give me this equation H plus rho k I into E, and this you can see in both the equations k is common. So, as far as error is concerned, the k cancels out. So, the error evolution from kth step to k plus half step is entirely determined by the structure of H and V matrix and by the way we have added this acceleration parameter rho k, right. And in the second half we go from k plus half and we arrive at k plus 1 step. So, that is what my error is. So, if I now combine both the steps, then what do I get? E k plus half would be V plus rho k I inverse operating on this, and there is this minus sign sitting up front operating on E k plus half. But from the first equation I can get E k plus half is nothing but minus of H plus rho k I inverse into this. So, that is precisely what we have done. So, what we see that one step of ADI involves the error to migrate from E k to E k plus 1 through this matrix T of k, which I have called it as the error reduction matrix. And you can very clearly see what this T of k is. T of k is this whole set of this product of this 4 matrices, right. Please do understand that when I write this inverse, it is not such a great difficult task to undertake, because these are tridiagonal matrix. We have exact solution by Thomas algorithm. So, that is not a question that we should be bothered about. So, once I see the error at successive steps are related by the error reduction matrix, then I can form a kind of a norm for measuring them. So, that is what is written here, that the error at the k plus 1th level is bounded by what was my error at the previous step times the norm of the error reduction matrix. There are various ways of defining the norm, but we have already seen that we do it in terms of the spectral radius, right. We have done that, but nonetheless we will still figure out certain interesting properties of this. Please take a look at the previous slide. The in definition of this T matrix, the V matrix appears in the beginning and in the end, okay, and H matrices are sitting in the middle, right. So, that is little unwieldy, and that unwieldy structure can be rectified by performing a similarity transformation. One of the property of similarity transformation is that if I have a matrix, I perform a similarity transformation, the eigenvalues, eigenvectors do not change. Okay? You have to take it from me. I am not going to say more than that. This is a well established result, that if I perform a similarity transformation, how do I perform a similarity transformation? I take the original matrix T that we have here, okay, and then I pre multiply by the matrix and post multiply by its inverse, right. So, that is what we have done. We have actually done here that V plus rho k I multiplying T and V plus rho k I inverse post multiplying that. Then what happens? I can put in the expression for the T matrix shown in the braces, and then I get this. See, now actually what has happened, I have a sort of a pair of product term, first of which is totally dependent on H matrix, the second is dependent on V matrix. Okay. So, this T tilde matrix that we have obtained is determined in terms of this one, this particular product form. Now, if I look at the tridiagonal matrix with that property that we have discussed, we can show that the eigenvalues of those matrices will be real. The entries are real, plus those properties that we have enunciated, they will ensure that we will have real eigenvalues. So, if I have the eigenvalues of H and V matrix as mu and nu, then I can see that the eigenvalue of this T tilde matrix would be given by this. So, instead of H, I will write mu. So, this first factor is mu minus rho, and this is inverse. So, that will go in the denominator, mu plus rho, right. And the second factor will give me nu minus rho, and this inverse will go downstairs to give me nu plus rho in the last expression. Why have we written like this? It very clearly shows, irrespective of whatever may be the value of mu and nu to be, each of this product within the first bracket is guaranteed to be less than 1. Can you see that? That whatever may be my value of mu and nu here, whatever may be the value of mu and nu, this factor as well as this factor is always less than 1. Can you see that the tremendous benefit that we have derived out of this particular operation? That whatever may be the spectral radius of H and V matrix, they could be quite not so well behaved. They could be very close to 1, so that it will struggle like what we have seen. Even then, these factors are, each one of them are always going to be less than 1. So, basically what does it imply? That is understood here, that my error in successive iteration is moderated by the norm of the T matrix, and that norm of the T matrix we have just now ensured is guaranteed to be less than 1. So, this shows a nice convergent iteration. So, in doing that, what we need to do is of course find out the eigenvalues of H and V matrix, and we have to also find out what this rho is, that acceleration parameter that we talked about. Now, look at the way that we have written down that linear algebraic equation, that E k plus 1 is related to E k by the multiplication of t. Now, if I do L such iterations, so I go from E k to E k plus L, then I find it is nothing but taking a product of this successive t matrices. And this is where we also note that earlier also I had added a subscript with rho, here also I have added a subscript with I here, rho I. It means that from on each iteration I could take this rho to be different. Okay. How do you choose it? We will come to that, but there it shows that we have added degree of freedom in choosing that acceleration parameter rho I, so such that the error after Lth iteration is determined by the eigenvalue of this product matrix of t. So, I would have t of rho 1, t of rho 2, so on and so forth up to t of L. That is what this product operation is signifying. So, if I call the eigenvalues of that product in terms of lambda, now lambda is a function of those eigenvalues of the constituent H and V matrix, so mu and nu. They will look like this, and they will also depend on the acceleration parameter rho I choose. So, I goes from 1 to L. So, if I look at the norm or the spectral radius of that lambda matrix, that would be given here. Let me call that as capital lambda matrix. So, that would be nothing but take this product form and look for its maximum value when mu and nu take its successive values. How many values of mu and nu we will get? That will be determined by the dimension of H and V matrix, right. If I have a H matrix which is dimension is n by n, then what do I get? I will have at most n distinct eigenvalues, right. So, that is precisely what we are doing. We are scanning through all those m and n eigenvalues of mu and nu and trying to find out what is the maximum of it, because we know when we adopt this strategy eventually what will matter is the spectral radius of this product matrix, right. Now, let me draw a diagram to tell you what we get out of this operation by this T matrix. See, what we have written down just now is that E k plus 1 is given by the T matrix. So, this is a vector and this is operating on this. Now, what we found that this itself in a norm fashion, this gives me like mu minus rho I, mu plus rho I and nu minus rho I and nu plus rho I. Let us look at one of this factor. Let me plot this. On this side, let me plot it as a function of rho, okay. And on this side I am plotting, let us say mu minus rho I by mu plus rho I. Now, if I choose rho I as one of the eigenvalue of H matrix, what will happen? The numerator would be equal to 0 for that eigenvalue, right. So, if I am choosing a value rho I equal to rho j equal to let us say call that as mu j, that is what I am going to get for that combination. So, for different values of well, I think I should have plotted mu here, the whole spectrum of eigenvalues that we are looking at. We are trying to find out what this factor does for different spectral component of this eigenvalues. What happens is that value, when that acceleration parameter coincides with one of the eigenvalue, that is where this factor is 0. Anything that is less than this will go like this. So, the fact that I could choose a acceleration parameter coincident with one of the eigenvalue annihilates that component of the error, because that is where this is 0. So, this is your 0, and where do you get the maximum? See, if mu goes to infinity, then of course, the value will saturate to at the most 1, irrespective of whatever rho you choose. So, what we are finding out that this is the kind of picture that we get. So, all such choice of rho acceleration parameter we make actually brackets the corresponding error component between 0 and 1, and that is exactly what we wanted, right. That is the whole idea of error reduction. So, what happens is, then if I have, let us say, mu 1 to mu n, what I could do is I could keep choosing my rows as those eigenvalues themselves. If I choose rho 1 equal to mu 1, then I know on that iteration any error that is proportional to mu 1 has been taken care of, right. So, this is the whole idea of looking at it, and we are also being assured here by this expression that what happens is essentially is the spectral radius of this is what matters most, and that is what we want to do. But think of the possibility that if you have taken, say, 500 point in the x direction, 500 point in the y direction, you have to calculate 500 eigenvalues, for H matrix, 500 eigenvalues for V matrix, and we will be doing this iteration. First time you will take mu 1, then next you take mu 1 equal to rho 1, then mu 2 equal to rho 2, rho 2 equal to mu 2, and so on and so forth. But then you are expecting to annihilate all these error component, you have to take the full cycle, 500 such things, and that is a luxury. For each step of solution method for elliptic equation, if you have to take that many number of iterations to take care of one cycle, then you are in dire strait. If I have to do that, most of the computations will come to a halt. What we try to do in our regular day to day activity, we try to get it within 5-6 iterations. If it is not done, then we know we have a slow method, we have to improve upon it. So, what it actually tells, that even if I know all the eigenvalues of H and V matrix, it is not very practical to use all those informations up. What you are of course noticing that when I choose, say, mu j equal to rho j equal to mu j, I have a whole set of range over which, let us say, this is something like 0.2. So, this range, all the error component has been reduced by 80% in that step, right. So, what I could do is a choice of a selective such points would take care of not only that particular point, but also its neighborhood. So, I do not need to exhaust all the eigenvalues themselves. I could take some selective values, and that is what I state here, that practical estimate, how many such values we should take, how should we go about it, that is guided by this statement that we have the eigenvalues whose ranges are given. Let us say the mu ranges between a and b, and nu ranges between alpha and beta. Then what we will do is we will try to find out a sensible number of such acceleration parameters lying between these bands, and we will try to work it out. And how do we do it? Well, we want to automate. So, what we try to do is we try to find out the minimum of a and alpha, here and call that as A bar, and the maximum of B and beta that we call as B bar. We can find out their ratio, that is like something like your stiffness ratio, right. If you recall, in the discrete equation I had that form h by k, k by h. So, what you find here also, I am talking about how the problem is stiff in the x direction, how the problem is stiff in the y direction, that is given by this eigenvalue spectrum, that is determined by A, B and alpha and beta, and the ratio of this global maximum and minimum determines how fast it can be done. So, Peaceman and Ratchford actually suggested that we do it like this. We take a sequence of n of those acceleration parameters. I have indicated with a superscript p to indicate that is due to Peaceman and Ratchford, that is given by this. So, what you are doing actually, you are taking n such acceleration parameters between A bar and B bar, that exhausts the whole possibilities, right. A bar is the lowest value, B bar is the highest value. So, that is what you do. Well, there is a bit of mathematics that goes behind all this, and how do you choose that n? There are a couple of ways. Varga and his colleagues have shown that if you know this ratio A bar by B bar, that is C, then you should choose n in such a way that this inequality is satisfied, that root 2 minus 1 raised to the power 2n should be less than or equal to C. There was another person, Waxpress, he suggested the alternative form, and what we get is much higher rate of convergence by adopting this method. Now, what is it that remains to be settled is how do I find out those quantities given in the first line, the minimum and maximum of an eigenvalue, without sweating too much. We have to compute, and we cannot do much with trying to find out the eigenvalue spectrum of a 500 by 500 matrix. That is too much. That itself is a problem which is maybe 1000 times more difficult than your original problem. So, you do not want to do that. So, that is where there are a couple of theorems due to Gershgorin that comes very handy. This is very practical and very useful, and let us use it. Okay. So, what we have is, let us say I have a matrix A. So, I can write down all those quantities A11, A12 and so on and so forth, A1n and A&n. So, let us say I have a full matrix like this. The first theorem says that you can find all the eigenvalues, every eigenvalues of this matrix A would lie in the union of circular disks, and the circular disks are formed in the way that the center is located at the diagonal. So, if I have a AII, so this is where the center would be located. So, basically what we are talking about is we are trying to find out the eigenvalues of A. So, I will plot lambda imaginary and lambda real, and what I would do, I will look at, let us say, the ith entry of that, and I will find out the center of that circle, that is at a distance AII from the origin, and then the radius of the disk that is formed, that is given by this. So, this radius is nothing but the sum of the magnitude of all the off diagonal term in that row, right. So, I could add say AI1, AI2 and so on and so forth, and I sum it all up by taking its magnitude here. Of course, this is this excludes the I equal to j point, and then I get a disk corresponding to this row. What I do is I keep plotting all possible disks So, I have this union of disks, okay, corresponding to each row. Now, the maximum and minimum eigenvalue would correspond to the global minimum and the global maximum. So, all you have to do is take a look at that matrix, see what the entries are, perform this, construct this disk, and this is not very difficult to do, because looking at the diagonal I know where the center is. I can take the modulus of the off diagonal entries, sum it up, I have the radius. So, for that row I know the minimum is here, maximum is here. Then I look at the another row and then compare this minimum and maximum. So, I keep on enlarging my union of the disk and find out what is the global. So, that is it. That is a very, very easy task to do, and in the present context it is so much simple for you to do, because it is a tridiagonal matrix. Your matrix has full of zeros. So, all you will have to worry about the diagonal term, that is your center, sum that 2 off diagonal term, that will give you the radius. And what have we seen? Sum of this off diagonal term balances the diagonal term. You recall that we had written that. So, what happens? We actually end up getting a disk which actually touches this point, right. So, you will get the center in the middle, diagonal term in the air, and the off diagonal term will determine that. So, that is rather very, very easy for one to do that. I think we will continue this discussion. I hope you will remember after your nice holidays. We will talk about it. We are not done yet. We will talk about little more on ADI method. Now, you know what ADI method is. We will talk about another method which is of contemporary interest and use, that is called the multi-grid method. We will talk about that.